today's lecture we will discuss about capacitive sensors. So, how to use the capacitive sensors, how to do the signal conditioning for capacitive sensors, and then and its various applications also we can discuss in today's lecture. So, our topic would be capacitive sensors. Now, the capacitive sensors are very popular nowadays because they are because of it is a small size, small in size, and then low power consumption. Because of these two reasons, they are very popular. Earlier, this capacitive sensor were not popular mainly because signal conditioning is very difficult, and they normally were picking up lot of noise. So, the disadvantage with the capacitive sensors are disadvantage is actually mostly noisy, and signal conditioning is difficult. Signal conditioning is difficult. So, but nowadays these problems are overcome, and now capacitive sensors are used extensively. For example, even our vernier caliper and all the capacitive sensors are used, and then they finally give a digital display of displacement in the vernier caliper. That level of usage are come for capacitive sensor, and capacitive sensors will be used more and more in future. Because it is of low power consumption and of very small size. So, let us see the problems associated with the capacitive sensors. Now, basically capacitance actually is given by basically two plates operated by a dielectric, which already discussed, and then the distance is d, and then the C actually is given by epsilon naught epsilon r A by d. So, that one can use this capacitive sensor either for area variation, because if A varies, then capacitance also changes, where A is the area of the plate, d is the distance between the two plates. Now, so obviously the two possibilities I can use as a sensor either for area variation, that is, if I vary the area of the plate, then the area variation can result in a capacitance change, and that capacitor can be used for sensing. So, area variation can be used, wherein you vary the distance between the two plates. You have one plate here, another plate here, plate 1 and plate 2, and then for example, if one is more related to the another, then the effective area what you have here, effective area varies. So, effective area changes with displacement. Other possibilities, space variation, distance variation. The second possibility is space variation. That is, we can have two capacitor plates and keep the area same and vary the distance d, the distance between the two plates. So, here distance between the two plates are varied, and keeping the area constant, distance between the two plates varied, and A is kept constant. So, this is space variation can be also used. There is another method possible, that is actually proximity variation. You can also use this technique, proximity variation. In this case, what is normally done is that you have two plates, then that is another third plate, grounded plate. Now, I will have a here one plate, another plate, then you have a capacitance between these two, that is the C. Then you have actually capacitance between this and this Cg. So, when the ground plate, this is a grounded plate. So, when the ground plate this distance varies, for example, this distance d, if the distance between the distance between the ground plate and the active plates say P1 and P2, the distance between these two varies. For example, I can move the ground electrode. If I come very closer and closer, you find that this capacitance is decreasing, and if I go more move away, then this capacitor is actually, and also as I come as I move more away, then this capacitor is increasing. So, this actually, this also can be used to sense the displacement. So, here in here grounded electrode is moved, grounded electrode is moved, and capacitance between the two fixed plates are measured, fixed plates. So, this because of proximity effect this happens, and then here this technique also can be used to measure the displacement. So, essentially we can measure the displacement either by area variation method or space variation method or the proximity effect, using the proximity effect. Now, we will see in each of this how that can be used for a different purpose. Now, let us see a general capacitance measurement technique first using op amp, because earlier we have discussed capacitance measurement using a ratio transformer technique, that is the earlier discussions were about using ratio transformer technique. Then we also discussed about diode pump circuit. Now, we discuss about how to use op amps effectively, for capacitance measurement. Because this is what now we are going to discuss more in this lecture. So, how to use op amp effectively for capacitance measurement. So, if you recall our earlier technique, that is the ratio transformer technique, there we could able to measure the capacitance accurately, mainly because we were able to remove the ground capacitance, because if we have a capacitance like this, and then we had shown that you can have a detector here, and if the detector is detected here, then this capacitance C1 and C2, C reference is here, then you have a detector here, and this is energized with the AC source. Now, this actually V1, V2 you had, and then normally what was done in this circuit was this is a ratio transformer bridge, is a ratio transformer. In this case, we varied the center tap such that you get a null at the detector. So, for example, if C1 and CR are equal, then you will get V1, V2 are equal, because the current actually flowing like this, and this current actually flowing like this. So, if both the currents are equal, then it will actually balance out, and that way V1 the current comes as V1 C1 omega will be equal to V2 C2 omega, that is what we get, and V1 by V2 will come as C2 by C1. And in this method, the stray capacitors were removed. Actually, this stray capacitance which had at the two ends, this is capacitance measurement. So, it has this stray capacitance 1 and the stake capacitance 2. This they do not contribute for the balance, because this capacitor is actually powered by the source. The source is a low impedance, so it has no effect, and this capacitor actually sends only the detector. So, at null point there is no current through this. So, the stake capacitance has no effect in this method. Stake capacitance has no effect. Capacitance no role to play in the balance, in the balancing of the bridge. So, it is very accurate. However, balancing the bridge is the main issue. So, that is why this is not very convenient for instrumentation work. So, balancing is a balancing to be done manually. This is the main drawback of this circuit. Main drawback for instrumentation work. Now, people are not using this very much, except that standard equipments where we can manually balance the bridge by wearing the center tap. We also discussed about this earlier. Now, the next technique that was came was that diode bridge pump circuit, wherein that you have a square wave and connected to the capacitor like this, and then we had a voltage coming here, and then output this is the output voltage. You have output you have resistance here, and the capacitor, this is capacitor under measurement. So, this is the capacitor under measurement. This is a diode pump circuit. This is capacitance under measurement. Now, in this case, the square wave source of voltage V actually goes 0 to say 5 volt or 15 volt. So, if you have this one, then initially this source, when it is going positive, it charges up this capacitor, and then when it drops to 0, then this capacitor discharges to this. So, it finds a path like this and discharges. So, the energy is when it is high, the capacitor is charged, and when it goes to 0, the capacitor discharges the charges to the output capacitor, and then the output capacitor voltage builds up, and that also leaks through this R naught. So, we had shown earlier the total charge transferred, if frequency is f, the frequency of the source is f, if f is the frequency of the source of voltage V, then total charge transferred, per second would be C into V into F, because C is the capacitor measurement and it is charged to V. So, quantum of charge that it one cycle is C into V, and the total quantity becomes CVF, and so it continuously delivers charge to the output capacitor. So, this much of charge is delivered continuously to the output capacitor C naught. This charge is delivered to the output capacitor. So, if output voltage is V naught, then the amount of charge leaving the leaking through R naught would be, the amount of charge leaking through R naught would be the quantum amount of charge leaking through R naught would be equal to V 0 by R naught. So, this must be equal to the this must be equal to incoming charge, that is equal to CVF. So, essentially CVF is actually become V 0 by R naught. So, you will get output voltage in terms of capacitance. So, CV R naught F becomes V naught. So, C actually can be written as V naught by V into R 0 F. So, the capacitance out from V naught we can find the value of the capacitance. So, this circuit works well, but not good for very low capacitance, because few hundred PF it is good, because the capacitor is getting charged, and then as it discharges to this voltage rises up, output voltage rises up, and then this capacitor does not discharge fully, because the whatever voltage that is here, that much voltage is lost. So, ideally it is it assumed to be linear, but in reality that since this voltage is slowly increasing, it is non-linear, it can be made linear only if V 0 is kept very small. So, this is true only if V 0 is small compared to V. So, this is valid, only if V 0 is small compared to V. So, normally we can select R naught to keep V 0 few millivolts. So, keep V 0 for within few millivolt by selecting R naught. So, this error is there, plus there are also other errors, because you have the diode is conducting, and then if you have a capacitance at the other ends, for example, if you have a capacitance from here to ground. Now, this is charged and discharged through this one only. If you have a capacitance here, because the capacitor that is under measurement, that is this capacitor may have capacitance both the sides to ground, and this capacitor contributes little to the output, because when it is conducting, this capacitor is discharged, and then this capacitor getting charged along with this, and then when it goes 0, this also discharges, and even this capacitor also discharges, and this contributes little to the output. So, it is not very accurate, but nevertheless this is okay for purpose of 1 or 2% accuracy. It is good, it is good to have good for 1 to 2% 1% to 2% accuracy level. So, how to tackle the how to make measurements using a op amp. So, the third technique that what we are going to discuss in detail will be using operation amplifier. Now, if I want to measure the capacitance using operation amplifier, then one possible solution would be that I can have a ground, then I can have a capacitance here, then I can have a say sine wave source connected here, then have a output, the feedback resistance R and C, and the output voltage V naught. In this case, the current that is flowing through that, the AC source actually drives this capacitor, and current flows through that, and that actually flows through this R and then returns back to the ground. So, that develops a voltage V naught. So, the current I into R gives you the output voltage. So, the current I actually is given by, if this is V, then V into C omega, of course with J, and then multiply by R output voltage, that comes j V c omega into R. So, if we take the magnitude, that actually comes as the output voltage comes as V c omega R. That means, the output voltage proportional to capacitance C. So, output voltage is proportional to output voltage is linear to C, linear to C. Now, if we see our other earlier discussion, that the stray capacitance is always associated with any measuring capacitance, because you will have a capacitance from this point to ground, that mostly shield capacitor and other if you are using shielded wire, then we will always have these two stray capacitance with any capacitor. That is why the capacitor measurement is always considered as a 3 terminal measurement. That is, you have a ground terminal 3 and measurement terminal 1 and measurement terminal 2. So, if I consider capacitor 3 terminal device, so output voltage is linear to C, then always consider capacitor as a 3 terminal device, capacitor as a 3 terminal device. This brings 2 stray capacitances, 2 stray capacitances C1 and C2, that is C1 and C2. Now, C1 C2 are not producing any appreciable voltage at the output. This is because if you see the C1, that C1 is actually only loads the source. As long as source impedance is low, this C1 has no effect on the output. Similarly, this point is actually at virtual potential, because this is 0. So, this is also 0. So, no current actually flows through C2. So, C1 and C2 has no effect at the output. So, obviously, operational amplifier is a good device to measure the capacitance. Inherently, it removes the stray capacitance effect. So, the two stray capacitances, the two that is the C1 and C2, C1 and C2, C1 and C2 will not affect, will not produce any change in the output voltage, change in V naught. This is good, this is ideal case, but which is very nearly true, because as we are the main assumption is that here this has a zero impedance source, the zero impedance source, and this is also at ground potential. So, the validity of this assumption depends upon the source impedance and then the gain of the operational amplifier. Since the gain of the operational amplifier is very high, that invariably this is always true. So, so will not produce any change output. This actually comes, this is valid, provided it is valid, provided source impedance is 0, and virtual ground is really at 0, virtual ground is at 0, which is invariably the case. So, if you look at this, then the output voltage will be will give you a capacitance value. Now, if I use this capacitor for displacement measurement, this technique for displacement measurement, then what are the issues that we will encounter? Displacement measurement for so, if we take a displacement measurement, then we will be using this capacitance here, then another side we will be connecting the source of voltage V, and then we will be moving the distance. So, now the output voltage, which is actually V naught, and this is V, this R, and the V naught actually is given by V omega V omega C into R. So, if we take this is constant V R omega, then C actually can be written as A by D, and that constant we can write epsilon naught can be used. So, if D is varied, if for example D changes V naught varies by 1 by D fashion. So, this is not going to be truly linear for displacement, because as you vary the more and more D is varied, and this is going to vary in the 1 by R fashion. So, even though C varies actually, even though C is varying, but the output voltage, for large distance output voltage will be very small. So, another issue is that if we take this one true formula, we will have V into omega R, and then epsilon naught epsilon R A divided by D, that is what we will be having it actually. Now, epsilon it is epsilon naught, not mu R. So, this is epsilon naught epsilon R. So, in real life, if we compare this output voltage with respect to ratio transformer bridge, here if V varies, that is the supply voltage varies, also output voltage will be changing, and the frequency of the source varies, also output voltage will be changing. And then if epsilon is relative dielectric constant, for example, if there is some moisture in between the two plates, then also you will have a output voltage will give a error. So, if we compare this output voltage with respect to ratio transformer bridge, that this is not as accurate as ratio transformer bridge, because so this is not as accurate as ratio transformer bridge. As accurate as ratio transformer bridge. This is because the errors are one V variation, epsilon R variation, omega variation. These are very serious problem, because epsilon R can vary because of moisture can create problem, and then source voltage can vary, frequency can vary. So, these problems are not there in the earlier circuit, that is the ratio transformer bridge circuit. So, we have to see how to minimize these errors. So, one possibility is you can go for two plate method, actually that is what that done in industry. So, two plate method, two plate, the three plate that is the three plate technique, capacitance with the capacitance with three plates, with capacitance sensor with three plates. What is done is that we can have this operation amplifier. We can have one plate, then the second one, and the third one. Now, this plate can be attached to our inverting terminal, inverting terminal can be connected, and we can energize this with for example, we can have simple transformer with the center tap. So, we will get equal voltages here and opposite voltage here. For example, we will have V1 here, V2 here, and the displacement actually moves the center plate back and forth x. You move the center plate here. So, you will have, for example, between these two you have capacity C1, between these two you have capacitance C2, and you have the resistance R. So, here this is energized with the AC source. Now, if you see this method, if you see this method, you will see that this actually sends a current like this, and then it goes like this. Then this current is reverse current, opposite. This voltage and this voltage V1, V2 are 180 degree opposite. So, the current through C1 and current through C2 are 180 degree opposite. So, basically the current through C1 and C2 are 180 degree out of phase. So, if the two currents are equal, then you will get the output 0, otherwise the net result would be. So, the current through C1 will come current through C1 is actually V1 C1 omega with the J component, and then current through C2 will be V2 C2 omega. And if we add these two currents, this is what it is summed up. So, you will have V1 C1 omega minus V2 C2 omega is what actually comes as a output voltage. So, that is the output voltage that you get here into R, of course, into R is what is flowing through this. So, if you simplify this, that it comes as V1 C1 minus V2 C2 into omega R. If V1 is equal to V2, then we can write V1 is equal to V2, because in the minus sign already considered. So, that makes it V1 omega R, V into omega R equal to C1 minus C2, that actually becomes V naught. But then C1 is coming because of one capacitor with respect to D. So, if I take, for example, the capacitor movement like this. So, if I take the center plate at the midpoint at D, if it moves to D plus x, then this distance is, if the plate moves like this, the center plate moves like this by x, then this distance plus x plus d, this becomes x plus d, and then this distance becomes x minus d. Because if I move the plate by amount x, then the distance for one plate to another, this becomes x plus d, and the other one becomes x minus d. So, consider, and then let us assume area of the plate is A. So, this area is A. So, considering area is A, area of the plates are A, and then the second one is x is the displacement with respect to the midpoint, x is the displacement from the center distance d. So, if I take this, then C1 can be written as, for example, this is C1 and this is C2. C1 will be epsilon naught epsilon r A by d minus x, and C2 will be epsilon naught epsilon r a by d plus x. So, that gives C 1 minus C 2 s C 1 minus C 2 s give epsilon 0 epsilon r into a. So, you will get 1 by d minus x minus 1 by d plus x. Which actually can be shown as epsilon naught epsilon r, and then you have d squared minus x squared, then you will have d plus x minus d minus x. This comes at C 1 minus C 2 s. So, that makes C 1 minus C 2 will appear as a epsilon naught epsilon r into d goes off, you will have 2 x by d squared minus x squared. So, C 1 then the output voltage, if you take it to the output voltage, that is in this formula we had seen that that output voltage V naught is given by V omega r C 1 minus C 2. So, output voltage can be shown as V naught will be V omega into a epsilon naught epsilon r into 2 x by d squared minus x squared. Even though it is linear with x, but then only for smaller distance when x is small only it will be linear, x V naught will be linear with the displacement. For small values of x, for x much smaller than d, then V naught is actually proportional to x. But then here again you will find that it is sensitive to omega, it is sensitive to variation in V, it is sensitive to actually that epsilon r variation what we have planned, when the moisture varies, then it is supposed to cancel off both. That is not really happened, because our capacitor currents are still there. Only if it is a null method, then it can be cancelled. But then here all these things still have effect. So, even this is not very accurate, and it as well is not very linear. So, is there any other method by which we can make it linear? Now, one possibility is if we go for area variation, then this circuit appears to be linear. So, let us see what happens for if I use the displacement measurement using a area variation. Suppose if I arrange the capacitor such a way that if for given displacement, area occupied by the common area occupied by the two plates are varying, then we see what happens. So, area variation. In this case, what you do would be that we will take the same capacitance sensor, and then here we take the two plates, then I will take the third plate like this, then connect to this to the third plate, then have this resistance R. And these two are actually similar to the last time. We will connect to two sources, that is I can connect center tap here and then connect one to this, then another to this. Now, this is the moving plate, you move this is the displacement d is moving. So, when you move this plate, then automatically when I move, for example, if I move like this by x, then area under this is coming down, area under this is increasing. So, you have two plates P1 and P2. So, when for a displacement x, for a displacement x, area under one plate is decreasing and equal area is increasing in the other plate. That is, if area is A, then in one plate becomes A into 1 plus x, the other plate it becomes A into 1 minus x. So, the area, that is how the area variation is taking place, that makes the capacity corresponding to the capacitance of the two capacitors also vary, and the current that is contributed by the two plates also will be varying. So, if you look at the current, that this actually sends one current through this capacitance and this sends a reverse current through this other capacitance. So, the net resultant current will be flowing through this. So, if we see the output voltage V naught here, output voltage V naught. So, if I see the output voltage, that actually will be the resultant of this one. So, if I have a VR omega into C1 minus C2 is what actually you will get as a output. It is similar to the last equation, but then C1 minus C2 if you try to find, that is where the difference coming. Now, the C1 would be C1 will come as epsilon naught epsilon r A divided by D, and then C2 would be here A is actually 1 plus x. I can make other ones epsilon naught A by into 1 minus x divided by D. Now, if I calculate C1 minus C2, so you will have C1 minus C2 will appear as epsilon naught epsilon r, and then you have A and D is constant is coming. So, you will have 1 plus x then minus 1 minus x, that actually will work out, that comes as you will have 2x. So, it is a wonderful thing because your C1 C2 that come linear with the displacement, because now we find that C1 C2 is linear with the displacement. Now, if I put this one in our equation for our output voltage V naught, that is here. So, this is our equation for output voltage V naught. So, if I do this, then V naught will come as V r naught V r omega into epsilon naught epsilon r A by D into 2x. So, output voltage linear with the displacement, output voltage linear for displacement. This is so output voltage is linear for linear for displacement x. This is good because we can have our output voltage measuring the displacement linearly. Of course, it is still sensitive to all the parameters that we can think of. You have your V variation, R variation, omega variation, everything still has a problem. So, it is also not as accurate as our ratio transformer bridge that we have discussed. So, this is also not as accurate as ratio transformer bridge. S I create as ratio transformer. Now, of course, this has this we got into linear, but linearity is there, but other variations are there. Now, there is one other way of looking this capacitance measurement, that is, can we go for a null method instead of looking at V naught, can we go for a null method, and then can the output voltage, if it is null, will this problem will be solved, or can we use instead of non-inverting amplifier, inverting amplifier, and see how the circuit can work. So, use of inverting amplifier, use of non-inverting amplifier. In the case of non-inverting amplifier, we can do this. For example, if I have a signal like this, I have this, then we can have this voltage. Then, for example, if I have a space variation here, for example, I have connect this. Of course, I put on resistance here, then I will get V naught here. So, here this is the voltage V. If it is under tap, then both voltages are V, one comes as V, one comes as minus V. Then again the current actually flow like this, and then this current actually flows into the reverse direction. So, if both the currents are equal, then you will get a 0 voltage. And if we have to use this method, then the capacitance that is present here, if there is a if the output voltage is present, then the capacitance that is present between this point and this point can create a problem, because we will have this is loading the circuit and creating the issue with this. So, this technique is not accurate, because it is sensitive to stray capacitances. So, this is not good, because it is sensitive to stray capacitance. Stray caps. If this method has to be successful, it should be a null method. So, this method, for this method to work, V naught should be equal to 0. This is very important actually. Otherwise, if V naught is 0, then this capacitor is limited, because if V naught is 0, this voltage is 0 and this capacitor has no effect. Then we have to modify the circuit to make it V naught 0. So, how to modify the circuit? How to make V naught 0? How to make V naught equal to 0? That is the question. Now, that we can do by using the feedback technique. What can be done is, we can have the op amp circuit, then for example, I can have this output, then one of the plates, for example, I can show like this. I have the source here, source I connect to this one plate, and this I connect to this. For bias current, I put this resistance at the input. Then whatever voltage that output voltage I am getting, that actually can be amplified. For example, I can have an amplifier here. I can amplify this, then I can sum it up with the feeding the minus voltage. For this I give this one. So, I will get minus V here, I will get minus V here, because this is plus V, and that is if they are equal resistance I put, then this becomes minus V. Then I can connect this minus V to this. So, we got plus V here and minus V here, the same as what we had done earlier, but then this whatever voltage that we are getting with the gain, that can be added at this point. That is feedback is provided to one of the capacitor input. So, voltage at this point consists of two parts, one is that minus V, then minus V, then minus V error, V error into gain. For example, if this is the error voltage V error, V error, and then this has a gain G, then whatever voltage is there, it is multiplied and then it comes VE into G here, and that is minus and put here. So, if there is too much for example, if this plate is close by, then the plus voltage will be more and you will get plus voltage more, that will increase this voltage, such that this the voltage is more, so that the more current comes here and the output voltage start coming down. So, by arranging this feedback network, one can make the circuit balance automatically, that is, if the gain is more, because if you write the equation now for C1 and C2, for example, if this is C2 and if this is C1, then you will find that the current, actually C2 current would be current through C2 through C2 is given by V into C2 omega, then current through C1, current through C1 is equal to you will have minus of V minus VE into G is what it is coming as a voltage, and then C1 omega. Now, obviously for null we have to have these two equal. So, we will have VC2 omega is equal to minus V minus VE into G into C1 omega. So, all that needed to be done is, if I since I equated this, we can remove the minus sign. So, we have omega can be removed. So, we have V into C2 that actually equal to V plus VE into C1 omega, or it can be even minus that, depending upon the polarity. This omega is gone, both sides is gone. So, it had done the balancing technique of the ratio transfer, because this term that if you see that we are adding now VE, if C2 is large, automatically VE is plus, if C2 is small, then VE is if C2 VE is getting with polarity is getting adjusted automatically, because the output voltage is inverted here. So, the bridge automatically balances out. So, by VE does the function of VE does the balancing technique. So, by this, now if I write then the bridge is getting balanced. Since the bridge is getting balanced, this capacitor is not a serious problem, the stray capacitor is not a serious problem, because if the VE will be small if the gain is large, VE is small if the gain is large, VE is small if the okay, VE into G, sorry, VE into V into G has to come here. Yeah, V, if gain is large, V is very small. If V is small for large C. So, this is actually, if you write the equation for C1 and C2, that C2 is actually is coming for displacement A by t plus x. For example, C2 can be written in terms of A and D. Similarly, C1 can be written in terms of A and A and D plus, for C2 can be written as mu naught is epsilon naught epsilon r A by t, and C1 can be written as epsilon naught epsilon r A by d minus x. Now, you will find that similar problem with what we had with the our is amplifier with non-inverting terminal. As inverting terminal also we had the same issue, but then by feedback technique we can avoid the balancing and bring the output close to 0, and then we can get rid of the effect due to this capacitor. So, one can use even the non-inverting amplifier also for balancing. So, non-inverting amplifier also can be used. Amplifier also can be used. Nevertheless, it will also, we will show whether it is linear or not linear in the next lecture. So, we will show in the next lecture whether it is linear or non-linear, whether it is linear or non-linear. For displacement x, that is V0, because it is a balanced route. So, the measurement also depends upon V1 and V2 measuring. So, we will see how this is measured, whether it goes linear or non-linear in the next lecture.